So let's keep going with our review here. So in that same, after we did local linearization, we learned how to find maxima and minima of functions. So if we consider the function f of x, x to the fourth minus 2x to the fifth on the interval from -1 to 1. So we want to try to figure out what we can about this graph. So let's find the critical points of f. And classify each as a local max, local min, or neither. So what's the critical point again? Derivative is 0, or the derivative is undefined. So in either case, we definitely want to start by finding the derivative, right? So f prime, we're just going to use our normal power rule there, 4x cubed minus 10x to the fourth. And can this ever be undefined? No. This is just a polynomial. We're not in any danger of dividing by 0 or any of the things that might make our derivative undefined. So all we have to do is do what with this? Set it to 0. And let's see, I would like to divide each side by 4x cubed. Good idea? No. We've seen many times that dividing is dangerous, and instead we should factor. So instead of dividing by 4x cubed, we factor out of 4x cubed. Not 4x cubed. How many x cubed? 2x cubed. And we're left with 2 minus 5x. But this we like, because now we have two real numbers being multiplied together that equal 0, meaning one of them's got to be 0. So if 2x cubed is 0, that means x is what? X is 0. And if 2 minus 5x is 0, x is 2/5. So these are our critical points, and we want to decide if each of them is a max, a min, or neither. How do we do that? Do a number line. So we put our two critical points on the number line. And then will I be plugging numbers into f or f prime? F prime, right? Because plugging into f would just tell me the value of the function, whether it's above or below the x-axis. We don't care about that. We want to know whether the graph is going up or going down. So we pick a number on the left of 0, like -1. And do I care what number I get for f prime? I only care about the sign. So I take a negative and I cube it, I'm going to get a negative. And 2 minus 5 is like saying 2 plus 5. So we get a negative times a positive, which is a negative. So what's f doing out here? Decreasing. Meaning x equals 0 cannot possibly be a local max, right? Because the graph would have to go up first. I could pick 1/5 in here. 1/5 cubed will give us a positive. 2 minus 5/5 is a positive. So we got positive, positive, which is positive. So f is going up there. So 0 did indeed end up being a local min, right? And what number can we pick out here? 1. And we get a positive times a negative, which is a negative. So f has a local min at x equals 0. And a local, what was the other one? Local max at x equals 2/5. Agreed? All right. After we find local extrema, we usually find what kind of extrema? Global. So let's find the global extrema. And what did we decide about global extrema? They could occur at a local max or min, but they could also occur where? At an endpoint, right? And so in fact, thinking about what this graph looks like here, the graph starts somewhere, comes down, then goes back up, and then goes back down. We see that the max, global max, could be where or where? Could be at this endpoint, which was -1, or at 2/5. And the global min could be at 0, or at this far right endpoint of 1. So we want to compare which of these 2 points is higher, and which of these 2 points is lower. So we plug into what? F, F prime, or F double prime? Plug into F. We want to know the actual values of the original function F. So we want to figure out what F of -1 is, F of 0, F of 2/5, F of 1. We're plugging into the original function. F of 1, we're going to take -1 to the 4th, which will be +1, minus -2. So I think F of -1 will be 3. F of 0 is 0. F of 2/5 is not quite as nice. So I'm going to take 2/5 and raise it to the 4th power. 2 to the 4th is 16. 5 to the 4th, 5, 25, 125, 625. 16 over 625. Then I'm going to plug it again into 2x to the 5th. So I'm going to get 2 times 2 to the 5th, 2, 4, 8, 16, 32, 64. And on the bottom, I'm going to get 5 to the 5th, 5, 25, 125, 625, 3125. Yes. I'd like to get a common denominator of what? 3125. Meaning I'm just going to multiply this by 5 over 5. 16 over 5 is 80. So I'll get 80 over 3125 minus 64 over 3125. So 16 over 3125. Of course, you have your calculators if you don't want to do that all in your head. And then f of 1, this should be easier. F of 1 is 1 to the 4th, which is 1, minus 2, so minus 1. So from that, we can conclude what? F has a global max where of all of these y values, 3 is the highest y value, so that's the global max at x equals -1. Oops. And a global min where? Global min at x equals 1. So in this case, they both ended up being endpoints, but that's not always the case, right? It could have been one of the interior points, one of the critical points in the middle there. So we had to check all of those points. Questions on finding global extrema. And after we find that, we usually find what? Inflection points. And remind me, what's an inflection point when F does what? When F changes concavity. And what's the easiest derivative to look at to figure out concavity? F double prime. So I've got two versions of F prime here, factored and unfactored. Which would be better to take the derivative of? Unfactored, so we don't have to use the product rule, right? So we'll just take the derivative of 4x cubed. That'll be 12x squared minus 40x cubed. And again, we should check to see if this is either what or what? 0 or undefined. Can this ever be undefined? No, it's just a nice polynomial. Can't be undefined. We set it to 0. Better to factor or divide? Factor. What can we factor out? 4x squared. And we're left with 3 minus 10x. 4x squared, thank you. So we got two things equal, product of two things being 0, we like that. 4x squared is 0 means x is 0. And the other possibility would be x to be what? 3/10. So these are our inflection points. Yep. Are these guaranteed to be inflection points? Have you ever seen an example where the second derivative was 0 and it wasn't an inflection point? Sure. You had a homework problem like that, right? How do we check if these really are inflection points? Do a number line. And now what will I want to be plugging into to figure out the concavity? I want to plug into 3/10. Thank you. 3/10. Please tell us, yes. Once it's on video, it's there forever. I know. We don't want the people at home yelling 10, 10, 10, not 8. What should we be plugging into here? F prime or F double prime? F double prime. What's a good number to pick out here? -1. We know that no matter what, other than 0, which we're not going to plug in, 4x squared is always going to give us a positive, right? So all we really care about is 3 minus 10x. So we plug in -1, 3 minus -10 will be positive. So F is concave what out here? Concave up. What's a good number to pick next? 1/10. So this will be positive. This will be 3 minus 10/10, 3 minus 1, which is positive. So was x equals 0 an inflection point? No. So good thing we checked, right? It's not enough just to find out where F double prime is 0. Then we can plug in 1. We get a positive times now a negative. So now F does change concavity. So therefore, the only inflection point is where? Is at x equals 3/10. Questions? All right. Well, this kind of problem was just a warm-up for our families of curves, right? Which are the ones we really enjoy. So let's consider the family of curves. F of x equals ln of x to the 2m, where m is a positive integer. We'll start with the critical points. It's a good thing to think about the domain of this function. What is the domain of ln of x? Just positive, right? So our domain here is x greater than 0. Right, we saw way, way back in week 2 that log is the inverse of the exponential function. Exponential functions have range that's positive, so the domain of the log is positive. Okay, critical point. We need f prime. What rule or rules will we need for f prime here? Chain rule, right? Because we have one function inside of another. So we've got something raised to the 2m. The derivative is 2m, and then do I change the thing on the inside or keep it the same? Keep it the same. And what's my new exponent? 2m minus 1. But chain rule says you're not done. You take the derivative of what now? ln of x. So the derivative of ln of x, which is 1 over x. And we're supposed to look for where this is 0 or a undefined. Now we have an x in the denominator, so 1 over x is undefined when x is what? 0, but our domain is positive. So do we have a critical point at 0? It's not in our domain, right? So we don't have to worry about that. So all we have to do is set this equal to 0. Now you have to reach back to your algebra skills. Can ln of x ever equal 0? Well, we want ln of x to be 0. How do we solve an equation like that? Exponentiate, right? We do e on each side. So e to the ln of x is e to the 0, because e to the ln of x is just what? X. And what's e to the 0? 1. Right? Ln of 1 is 0. Because e to the 0 is 1, so log flips the input and the output, right? So if e to the 0 is 1, ln of 1 must be 0. And can 1 over x ever be 0? No, because fractions are only 0 when their numerator is 0. So our only critical point is x equals 1. What should we do with that number line? What's a nice number we can pick on the left of 1? Yeah, it would be nice to pick 0, but can we pick 0? It's not in our domain, right? So we could pick, say, 1/2. So it's going to be what? 2m ln of 1/2 to the 2m minus 1 times 1 over 1/2. Right? That's our derivative. And all we care about is whether this is what or what? Positive or negative. Ln of 1/2 is what kind of number? So let's remember what the graph of ln looks like. Ln of x looks like this. So that's why ln of 1 was 0. But if I take a number over here like 1/2, what kind of output do we get? We get a negative. So here, I've got a negative raised to what kind of power? Yeah. If we take a negative to a even, we get a positive. If I take a negative to an odd, we get a negative. We know m is an integer, so what kind of number is 2m? Even. So what kind of number is 2m minus 1? Odd. So you've got a negative, so this is 2m is positive. This is a negative to an odd power, and this 1 over 1/2 is positive. And what's a negative to an odd power? Negative. So this whole thing is negative. Agreed? What's the number we can pick on the right side of 1? 2? Sure. So we still get 2m. Now we get ln of 2 to the 2m minus 1. But ln of 2 is what kind of number? Positive, and a positive to whatever is positive. So what's our conclusion? X equals 1 is a local what? X equals 1 is a local min. Ready for the inflection points? Let's just remind ourselves of what f prime was. F prime of x was 2m ln of x to the 2m minus 1 times 1 over x. What rule or rules will we need for this derivative? Chain and product, right? Because we've got a function inside of another function, that's chain, but we've also got multiplication there, which is product. All right, let's take the derivative of the first part. 2m is a constant, multiplying it stays. What comes down?
Multiplying it stays.
That's right, but what comes down is the 2m minus 1. And we get ln of x to what power? 2m minus 2. But chain rule says you multiply by 1 over x. But then there's still the other 1 over x from the product rule, right? So there's two appearances of the 1 over x here. When we took the derivative of ln of the ln to the 2m minus 1, we got 2m minus 1, ln of x to the 2m minus 2 times 1 over x from the chain rule. So this whole thing here is just the first of the four parts of the product rule, then times this 1 over x. Agreed? All right, then we get to leave the first part alone. 2m ln of x to the 2m minus 1. And we want to take the derivative of 1 over x, which we could make hard by using the quotient rule, or we could think of 1 over x as really x to what power? X to the negative 1. So the derivative should be negative 1 x to the negative 2, which is the same as saying times negative 1 over x squared, right? Which is the same you would get if you use the quotient rule. All right, these are always fun. This can be undefined when x is 0, right? We're dividing by 0 all over the place here, but 0 is not in our domain. So all we have to do is set this equal to 0. And we'd like to factor out as much as we can. So we've got to find terms that appear on both sides of the plus sign here. They both have a what? They both have a 2m. They both have ln of x to at least what power? 2m minus 2. Right? That's the smaller of these powers. It might help to just think about, like, suppose we knew m. Suppose m were 5. If m were 5, this would be an exponent of how much? 8. And this would be 9. So you would have factored out the ln of x to the 8th, right? And they also both had a what? They also both had a 1 over x. Yeah, so that's good. So we factored out a lot. They both have a 1 over x squared. We factored out even more. And after we do that, what's left from the first term? Only the 2m minus 1. And what's left from the second term? A what? An ln of x, right? Because this had one more power, one more in the exponent, and there's also a minus sign, right? So it's minus ln of x. Agreed? All right. So can 2m ever be 0? No. We've already decided that if ln of x is 0, that means x is equal to what? 1. That was from the previous part. Can 1 over x squared be 0?
Because.
Cannot be 0, because fractions are only 0 if their numerator is 0. So all that's left is to set this to 0, or 2m minus 1 minus ln of x equals 0, which is like saying 2m minus 1 equals ln of x. And how do we solve an equation with an ln in it? Exponentiate, right? Back to the second week. E to the 2m minus 1 equals e to the ln of x, which is x. Are these guaranteed to be inflection points? No, we have to do a number line. Which side of 1 will e to the 2m minus 1 go on, the left or the right? Because we know m is a positive integer, meaning the smallest m could be is 1. So the smallest this could be is 2 times 1 minus 1, which is 1. So the smallest this could be is e to the first power, which is 2.71828182845, dot, 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 dot. So we've got 1, and we've got e to the 2m minus 1. Lovely. Let's try to make our lives easier by plugging in here. 2m is always going to be what kind of number? Positive. What kind of exponent is 2m minus 2 going to be? Even. So if this is an even exponent, no matter what I put in here, I always get what kind of number from that? Positive. And I always get what kind of number from 1 over x squared? So all of this is always going to be what kind of number? Positive. So all we have to do is plug into this, right? So we really get quite lucky there. So f double prime, what number can I pick out here? 1/2. Just numerically, it would be easier to pick something like 1 over e out here, by the way, because you're going to plug into ln. But we can do 1/2 if we want. So f double prime of 1/2. All of that first stuff you just told me is positive. So then it's 2m minus 1 minus ln of 1/2. But ln of 1/2 we decided is what kind of number? It's a negative. So we're taking minus a negative, which is like adding, right? But 2m minus 1 was already what sign? Positive, right? 2m is at least 2. So we've got a positive minus a negative. That's a positive plus a positive. So that's a positive. So what's the concavity of f out here? Concave up. What's the number I can pick between 1 and e to the 2m minus 1? So you're going to divide this number by 2. Let's make sure that happens. What did we say the smallest that 2m minus 1 could be? The smallest that 2m minus 1 could be is 1, right? So this is at least e to the 1, which is 2.7 something. If I cut 2.7 something in half, I'll definitely be on the right side of 1, right? So we could do 1/2 e to the 2m minus 1. We'll get a positive 2m minus 1 minus ln of that nice number you just told me. And now it's going to be time to use your log rules. Back to the second week. We've got ln of a times b here, right? What's the rule for ln of a times b? ln of a plus ln of b. So this is like saying minus ln of 1/2 minus ln of e to the 2m minus 1. But what is ln of e to the anything? The anything, right? They undo each other because they're inverses of each other. So this is like saying minus 2m minus 1. Right? ln of e to the 2m minus 1 is 2m minus 1. ln of e to the bananas is bananas. ln of e to the w is w. So we've got a 2m minus a 2m. They cancel. We've got a minus 1 minus a minus 1. They cancel, meaning this whole thing is just a positive times negative ln of 1/2. But you told me ln of 1/2 was what kind of number? Negative. So negative ln of 1/2 is positive. So was 1 an inflection point? No. It was a lot of work to figure out that 1 wasn't an inflection point. But it was worth it. So the algebra, as usual, is a little complicated with families of curves. Yep. Question? About what?
He said the algebra may be a little complicated.
The algebra may be, the algebra may be complicated, but it was worth it. I think we would all agree. What number could I pick on the, what number could we pick on the right out here? Thank you, Raymond. What number could we pick on the right out here? We could multiply it. By the way, another thing you could do is, if you remove this -1 from the exponent, that makes the exponent bigger, right? Which therefore makes the entire thing bigger. That'll be a little cleaner algebra, but I know that lots of us like to just double something, so we'll try it with the doubling. But the algebra will be cleaner if you just made it e to the 2m. All right. But this will end up being pretty much the same, sort of figuring things out here. Everything is the same except that instead of where we had a 1/2, we now have what? 2. So everything is going to cancel exactly the same. So we'll get a positive, and then 2m minus 1 minus ln of 2 minus 2m minus 1, meaning it'll all simplify to just a positive times what? Negative ln of 2 now. But ln of 2 is positive, so negative ln of 2 is negative. So we finally got an inflection point. Questions on that fun problem? Yes? Could there be a scenario where there's no inflection point? Definitely. I think there, yeah. I think one of your practice exams, didn't it have a problem that said something like show that there's no inflection point? I think there was one. I mean, you can imagine just drawing a graph that just is always concave up or always concave down, right? Other questions on families of curves? All right, let's do something more fun, like optimization. So what are the dimensions of the cylinder of largest possible volume that we can put inside of a sphere of radius 10? So the official thing is to say that it is inscribed, that is to say written within, drawn within, inscribed in a sphere of radius 10. Oh, largest possible what? Something. Volume. Largest possible volume. So with any of these optimization problems, we want to keep straight what our goal is right from the start. So in this case, the goal is to do what? Maximize or minimize? Maximize the what? Maximize the volume. And as usual, I will give you any complicated geometric formulas like the volume of a cylinder. But a cylinder, you're just taking a circle and then you're sort of giving it some height, right? So what should the volume of a cylinder be? Pi squared pi r squared times h, right? But we would give you that on the test. Okay, so we want to find the max of that, meaning we want to take its derivative, but what's the trouble? Two variables, and we're still in single variable calculus, so we can't do that. So there must be some other information in the problem that we can use to get either r in terms of h or h in terms of r, right? So what's the only piece of information we haven't used yet? The radius of 10, right? So I think we can draw a picture to help us sort of see that. So if we take a cross section right through the center of the sphere, right? I'm just cutting right down through the middle of the sphere. When you cut right through a cylinder, what shape will the cylinder look like when you take a cross section through a cylinder? It'll look like a rectangle, just in 2 dimensions, right? So I've got some sort of rectangle here within my cylinder. And it should touch the corners right here like that. I just didn't draw a very good circle, I guess. So the h is the height of the cylinder. R is the radius of what? The cylinder or the sphere or both or neither? This letter R is the radius of the which? Cylinder or sphere? If you had a cylinder that wasn't inside of a sphere at all, would its volume still be pi r squared? Yes. And therefore r would be the radius of the cylinder. So if I'm drawing r is like going from here to here, right? So somehow we need to relate r and h. But as you were telling me, what's the one piece of information I haven't used yet? The 10, which is the radius of the sphere. So there's lots of ways I can draw the radius of the sphere, right? I could draw it from like right here to right there, or right here to right there, or right here to right there, or right there, or right there, wherever I want. What would be a particularly useful way to draw it that would allow me to relate r and h? Right, to where it touches, so one of these corners up here. So I could say, draw that line there. The length of that line I just drew is 10, right? And if there's only one theorem to know from geometry, it's what one? Pythagorean theorem. So can you see a right triangle for me to draw here now? Yes? Yeah. Okay. The 10 will be the what of the right triangle? The hypotenuse. So where should I draw my other side? Straight up like this. You could also have drawn it right here, right? Those are going to be the same. But so now I've got a triangle whose hypotenuse is 10, whose one of the bases is r, and what's this base? Half of h, right? H is this entire rectangle, so this is just half of h. So we need to relate r and h. And we do that with the Pythagorean theorem, which says 10 squared is r squared plus h over 2 squared. Right? This Pythagorean theorem has come in handy for us a lot. I hope you remember all the times we've used it. Okay. Given our formula for v here and our desire to make our algebra as simple as possible, what would it be good to solve for now in this equation? R squared, right? If you try to solve for h, you're going to have to get a square root over here. So let's solve for r squared instead. So this is 100 equals r squared plus h squared over 4. So 100 minus h squared over 4 is r squared. As usual, it'll work if you solve for the other thing. It'll just be much, much messier. You'll be using the product rule and the chain rule. So as usual, if you take a minute to think here, which is the better variable to solve for, you will save yourself much more than a minute later. Okay. So now I can write the volume entirely as a function of what variable? V of h. Volume is pi r squared, which you just told me. Pi r squared h. And should we take the derivative the way it's written? We could, if we wanted to use what rule? Product rule. You're also quiet. Have we made a mistake? No. Okay. But do we want to use the product rule? Yeah, why not? So let's multiply out 100h minus h cubed over 4. Will that be easier to take the derivative of? So as usual, if you can simplify, you can often, not always, avoid product and quotient rules. Not always. Well, that's good. We've got our formula for v. What can we do with it? What's almost always the answer in a calculus class, a first semester calculus class? Take the derivative. So now, v prime of h, pi is a multiplying constant. Does it stay or go? Stays. Derivative of 100h is, I think, just 100 minus 3h squared over 4. Can that ever be undefined? That's just a parabola. Can't be undefined. So all we have to do is set this equal to 0. When will pi be 0? The world would be a very strange place if pi were 0. The ratio of the circumference to the diameter would be 0. So that must mean that the thing inside the parentheses must be 0. So that must mean that 100 must equal 3h squared over 4. Meaning if I multiply both sides by 4/3, I get 400 over 3 equals h squared. And then I take the square root of 400 is 20 over the square root of 3, or the negative, right? Because as we've talked before, when you're solving an equation like h squared equals 9, there are two solutions. But then let's remember what we're doing here. H is representing a what? A height. Have you ever seen a height of negative 20 over square root of 3 meters? Neither have I. So we can ignore that. And are we guaranteed this is what we want? We don't know, right? This might actually give us the what volume? This might give us the smallest possible volume, in which case the max would have to be at an endpoint, right? We've seen an example where that happens, so let's check. So now I can pick a number on the left, like 0. I'm plugging into what? V or V prime? V prime. So when I plug 0 into this, I get a positive. Is that good or bad? Well, I guess it's neither good nor bad. I mean, but if we're hoping that this is going to be the max, is that good? That's good. And if I pick a bigger number, number bigger than this, like say just 20, I plug in, I get a negative. So yes, it is the max. And have we fully answered the question? No, because it asked us for the what? Dimensions. So h equals what we just found, 20 over the square root of 3. And do we have a good way to find r? Not so great. We have r squared here, right? But we can solve for, if we solve for r, here will be the square root of this. So r is the square root of 100 minus h squared over 4. If I square h squared, I just get 400 over 3. 400 over 3 divided by 4 is just 100 over 3. 200 over 3. Okay, fine. Square root of 200 over 3, which is like saying 10 square roots of 2 over the square root of 3. For some reason, I've written down in my notes 20 square root of 2 over square root of 3. So does anyone see if there's a mistake somewhere? It's possible that I wrote it down wrong. All right, let's take a break and see if we agree with this. All right, everyone, welcome back. Our last bit of the review here. So in this problem, we've combined several topics into one. So find the following. And the first one is a limit. X goes to infinity, 1000x squared over 1.1 to the x. So if you just start and look at small values of x, the top is much, 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 much bigger than the bottom. But we're going to go all the way to infinity. And as x goes to infinity, what does the top of the fraction go towards? Infinity. And what does the bottom go towards? Infinity. So is the answer 1? It might be, but we don't know, right? Do we have a way to determine what infinity over infinity works out to be? Yes. What do we call it? L'Hopital's rule, which was really discovered by whom? Bernoulli. And L'Hopital's rule has nothing to do with the quotient rule, right? If somebody asked you what's the derivative of this function, you would have to use what rule? Quotient rule. But if somebody asks you what is the limit of this fraction, we use L'Hopital's rule, which says just take the derivative of the top, which is 2000x. And what's the derivative of the bottom? 1.1 to the x ln 1.1. So now the top is going towards where? Infinity. And the bottom? ln of 1.1 is some very small positive number, right? But some small positive times infinity will still be infinity. So what do? Do it again. Now the derivative of the top is just what? 2000. So is there any chance of doing L'Hopital's rule again? Impossible, because we cannot get 0 over 0. We cannot get infinity over infinity. So that's the end of that. And the bottom, what's the derivative of 1.1 to the x? Well, we just did that. It's 1.1 to the x ln 1.1. And this other ln 1.1 is a multiplying constant, right? Even though it's written on the right side, whether it's written on the right side or the left side, multiplying constants do what? Stay or go? They stay. So that's another ln of 1.1. So ln of 1.1 is something like 0.09. So I've got 0.09 times 0.09 times something going to infinity, which will all be going to infinity. 2000 divided by something going to infinity will go to 0. So in this case, even though when x is very small, if you graph this function, or not even that small, the y values are getting quite big. In the end, the bottom wins, and the y values come down towards 0. Questions on that one? Part A. L'Hopital's rule? Good. How about x goes to 0, sine of 2x minus 2x over 7x cubed. And as usual, if you are not absolutely certain that you know the value of sine of 0, cosine of 0, things like that, please use your calculator. In this case, sine of 0, actually in all cases, sine of 0 is what? 0. So the top is going to 0, the bottom is going to 0. And we know that any number divided by itself is always 1. Is that right? Well, any number except what divided by itself is 1, except 0, right? 0 is the only number that divided by itself is not 1. Luckily, we have whose rule? L'Hopital or Bernoulli's rule. What rule we need to take the derivative sine of 2x? Chain rule. So it'll be cosine of 2x times 2, or just 2 cosine of 2x. And the derivative of 2x is 2. And on the bottom, I think we get 14x squared. What? 3 times 7, I think, is 21. Thank you. All right. As x goes to 0, cosine of 2x goes to cosine of 0, which is 1. So we get 2 minus 2 on the top, which is 0. And on the bottom, we get 0. So what do? Keep going. L'Hopital's rule again. Derivative of 2 cosine of 2x is going to be what? Minus how many sine of 2x? Minus 4, right? Because the chain rule makes another 2 pop out. And the derivative of 2 is just 0. And on the bottom, we now have what? 42x. So the top is going towards 0. And the bottom is also going towards 0. Should we give up, or do you see hope? I see hope, right? Because what's the derivative of the bottom going to be now? 42. So we're done, right? There's no more chance of L'Hopital's rule. And if we apply the chain rule one more time on the top, we'll now get negative what? Negative 8 cosine of 4x. 2x. Boy. 2x. So the top is going towards what now? Negative 8, because cosine of 0 is 1. So we get negative 8 over 42, which, if we like, probably simplifies to something nicer, like negative 4 over 21. So in this case, as x gets closer and closer and closer to 0, the bottom of this function is bigger than the top by a ratio of 21 to 4, so about 5 to 1, and they're opposite signs. That's how we got the negative there. That's what that would mean in terms of the functions. Question? No. Any questions on that one? Let's do one more. L'Hopital's one more limit. X goes to 0, cos x minus 1 over e to the x. L'Hopital's rule? Top's going to what? 0. Bottom's going to 1. Could we use L'Hopital's rule if we felt like it? No. Do we need L'Hopital's rule? We all know that 0 over 1 since 3rd grade is 0. Since 4th grade? Phil didn't learn that until 4th grade. So remember, we can only use L'Hopital's rule for 0 over 0 and infinity over infinity. All the other fractions we know how to handle. Any questions on L'Hopital's rule or limits? All right, then we learned about integrating, right? So we learned how to find things like this. Integral of 1/3 plus x over 3 plus 3 over x plus 3 over the square root of 1 minus x squared plus 3 secant squared of x dx. Is this a definite integral or an indefinite integral? Indefinite, because there's no limits, right? Meaning the answer will not be a number, it will be a function, or actually a whole family of functions. This is telling us find all the functions whose derivatives are this. So what's the function whose derivative is 1/3? 1/3 x. And then we're going to use our rule here, right? Writing this x here is like writing x to what power? To the 1. And our rule for finding antiderivatives says we do the opposite for derivatives, right? So instead of subtracting 1 from the exponent and multiplying, we add 1 and divide. So x to the 1 will become x to the 2, and then we divide by 2, but we already had a 3 on the bottom, so now we have what on the bottom? 6. And if you take the derivative of that, do you get x over 3? Yes, you get 2x over 6, which simplifies to x over 3, right? That's how we can always check if we've got the right answer. Take the derivative. What about 3 over x? 3, and then we want to take the integral of 1 over x. What's the integral of 1 over x? ln, and let's not forget those crucial absolute values for half a point. Right? Because there's no way to know whether this x is a positive or a negative number here. All right, this looks familiar. This looks like it came from a what? 3, and then the one that has a positive square root of 1 minus x squared is what? Arc sine, right? So this is 3 arc sine x. Question? If this had been negative 3, then it would be 3 arc cosine of x. Or you could call it negative 3 arc sine of x, which tells you that the graph of arc sine and arc cosine must have a special relationship between them if one's derivative is the negative of the other. Those graphs must be flipped like this. What about 3 secant squared? That must have started off as what? 3 tangent. And at this point, you have what percentage of all correct answers? You have 1 out of infinitely many, right? So essentially 0%. But how do you get all the rest? Just that plus c gives you all the rest, right? Question? Why aren't the other x's absolute value? Why would they need to be? Like, are we allowed to plug a negative into x squared? Can you square negatives? Are we allowed to plug a negative into x squared, for example? Like, could you take negative 5 and square it? Yes. But could you take the natural log of negative 5? That's what's not allowed, right? So that's why that's the only one that needs the absolute values. All right. So that was an indefinite integral. Let's do a definite integral. 0 to 1, 7x squared, 4x cubed plus 1, all cubed dx. That looks awful, doesn't it? And although we've become really good at taking derivatives of awful-looking functions, taking antiderivatives of them is a lot harder. So we would like to turn this awful-looking function into something much nicer, right? And what's our technique for doing that called? U substitution, right? We've got to choose a nice u, which is an inside function, and hopefully its derivative will be somewhere else in the function. So in this case, we could choose u to be what? 4x to the third plus 1, right? Because that's inside of the cubing function. So this will become u cubed, which will be a lot easier to integrate, right? And what's the other clue that's good? What's du dx going to equal here? 12x squared. And we almost have that somewhere else, right? We've got 7x squared. So that's good. The fact that we don't have a 12, that we have a 7 instead, doesn't bother us, because we can always handle the coefficients by just pulling them in and out. The important thing is that there's an x squared somewhere. OK, so what can we do with this 7? Bring it out front. And then what's left inside is an x squared dx. But according to my nice formula from over here, where we just abuse this notation of du over dx and treat it as if it's a fraction, even though we know it's not, although we saw the justification for why this all works out nicely, and we have Leibniz to thank for this beautiful notation. x squared dx is really just what? 1 over 12 du. And you already told me that 4x cubed plus 1, quantity cubed, will just become what? U cubed times 1 over 12 du. So have you turned that awful looking integral into something much nicer? You sure have, right? The only thing left is to change the limits. So if x is 0, right, one of our limits was x being 0. When x is 0, what does u equal? 1. Right, because if I plug 0 into this, I get 4 times 0 cubed, which is just 0, plus 1. So u is 1. And the other x value that we need to check was what? If x is equal to 1, if I plug 1 in here, I get 4 times 1 cubed, which is 4 plus 1. So then u will be 5. So my new integral goes from 1 to 5 in terms of u. And that way we never need to substitute the x cubed plus 1 back at all. Or 4x cubed plus 1, I mean. So this is good. What can we do with that 1/12 inside? Pull it out front. So I've got a 7/12 out front. And I'm integrating from 1 to 5 u cubed du. So the fact that all the x's canceled means that we did a successful substitution. And the only question left is, have we done one that actually makes into something that we can integrate just by looking? Yeah. What's the integral of u cubed? U to the 4th over 4. Right? And remember, the fundamental theorem says, because you were able to find an antiderivative, you don't have to worry about all of those left-hand sums, right-hand sums, taking the limit of infinitely many rectangles. None of that stuff matters, all because we could find an antiderivative. All right, let's try to simplify this a little bit. 7/12 times 1/4 is really 7/48, I think. And then which of these numbers are we supposed to plug in first, the 5 or the 1? So we get 5 to the 4th. We already did that tonight, right? 625 minus 1 to the 4th, which is 1. And so that's 7 times 624 over 48. I think, if I was right, that works out to 91. 620 over 48 is 31. I mean, it's 13. 624 over 48 is 13. Yes, it is. Just chance that worked out to be an integer. Any questions how we do substitution to find a definite integral? Okay. We also used antiderivatives to find some things from the real world. Like if we were given the rate of change of some sort of real world quantity. So suppose we knew the rate of change of a population on some interval from 0 to 5 was given by the function 240 minus 15t squared people per year. And at t equals 0, the population is 5,000. And then we can answer all sorts of questions about the population, like what's its maximum, what's its minimum, what's its average. you understand what's happening here? So unlike the problems we did at the start of the year where we would have been given the population and asked to find its max or min, in which case the first thing to do would be to do what to the population function? Take the derivative. Should we take the derivative of this function on the board? This is already the derivative, right? So we've already got p prime. So the derivative of population is 240 minus 15t squared. So we just want to look for where this is either what or what. Zero or undefined. It's never undefined, right? It's just a parabola. So we just want to set this equal to 0. So then I think we get t squared. Boy, they don't make chalk like they used to. T squared equals 240 over 15. I think 240 over 15, luckily for us, works out to be a perfect square. Nice how that happens. So if t squared is 16, t is either 4 or negative 4, yes? And in general, it could be either, right? Time can be negative. It would just mean that it happened 4 hours before time 0. What time 0 was midnight or whatever. But in this case, what's our domain? 0 to 5, right? But if this had not, if we didn't have any domain, or the domain were, say, negative 5 to 5, then we would have to include both of these. But this is not in our domain. So does that mean that t equals 4 is the maximum when the maximum happens? No. For all we know, it could be the minimum, right? So how do we check if it's the max or the min? We do a number line. And we can do this even though we do not know a formula for p, right? All we need is p prime. So we pick a number less than 4 like 0. When we plug 0 into this, do we get a positive or a negative? Positive, meaning the population is increasing there. And if I plug, say, 5, I get 15 times 25, which is more than 240, so that's a negative. So what does that tell us about the max? When will it be? So the max is at t equals 4. And is that what the question asked for? No. The question actually asked for the what? For the population. So in a normal problem, from the first part of the year, we would now just take 4 and plug it into f, right? But we don't have f here or p, but can we figure out what p is? Yes. If this is p prime, so we need a formula for p of t. P of t is just the integral of p prime of t, so the integral of 240 minus 15t squared dt. So do you know a function whose derivative is 240? 240t. And then here we just use our power rule backwards, right? 15t cubed over 3, which is 5t cubed. But this isn't the only one. We have to put a plus c at the end, right? Right. But luckily we know p of 0 is what? 5,000. So when I plug 0 into this, I've got to get 5,000 for an answer. When I plug 0, this term becomes 0. This term becomes 0. So that's only going to work if c itself is what? If c itself is 5,000. That's the only way I'm going to get p of 0 to be 5,000, right? So we looked at all the different antiderivatives. We shifted up just to the right point so that we got the population at time 0 to be 5,000. Questions on that so far? And now what can we do with that? Right. So thus the max population is p of 4. And just for a sanity check, this number had better be more than what? Better be more than 5,000, right? We started at 5,000 and the population went up for 4 years. So when I plug in 4, we get 240 times 4, which is 960, minus 5 times 64, which is 320. So altogether, we get 5,640 people. Questions on how we found the max? After we find the max, we should find the what? What's the min population? But a lot of the work for us is already done. Based on our number line, what do we know about where the min is going to be? At one of the endpoints, right? The graph starts somewhere, goes up for 4 years, then goes down for a year. So the min had to be either at time 0 or at time 5, right? One of the endpoints, because we're talking about the global minimum. So from the number line, the minimum must be at t equals 0 or t equals 5. And how will we decide which one it is? We know p of 0 is already, we know that's 5,000. We'd like to know p of what? P of 5. So if I plug 5 into this, 240 times 5 is 1,200, minus 5 times 5 cubed, which is 625. 625 has come up a lot tonight. Plus 5,000. So we added 1,200. We lost 625. I think that means a gain of 575. So 5,575. So what is the min? So the minimum is 5,000. Questions on that one? All right, let's find the average population on this interval. The answer had better be between what two numbers? Better be more than 5,000, less than 5,640, right? If the highest you ever are is 5,640, there's no way your average can be more than 5,640. And if the lowest you ever are is 5,000, the average must be at least 5,000. Okay. So how did we decide that we find the average value of a function? Integrate and divide by b minus a. And what am I integrating here, p or p prime? P, because we actually want the average of p, meaning we want to actually add up all the populations at every instant all along the way, essentially. So we need to integrate the actual population, not the rate of change. Well, so is there the question was, does it matter if we do it this way or the shorter way? Is there a shorter way in this case? There would be a shorter way if the question had asked, what is the average rate of change, right? If we asked the average rate of change, then we would just take p of 5 minus p of 0, 5,575 minus 5,000 over 5, and the answer would be 115 people per year. That would be the short way to do that problem. There is no short way to do this problem. We actually have to go through the work of integrating it. But that's okay. We're good at integrating now, right? What's the integral of 240t? 120t squared. 5t to the 4th over 4. And what's the integral of 5,000? 5,000t. And could I put a plus c in there if I wanted to? Yes, because we're allowed to put any antiderivative we want. We're going to plug in the 5 and then plug in the 0 and subtract, right? So you get a plus c and then subtract the same plus c. So for the make our lives easy, we just leave the c as 0. And which one gets plugged in first, the top or the bottom? The top. 120 times 5 squared minus 5 times 5 to the 4th over 4 plus 5,000 times 5. Luckily, when we plug in 0, we just get what? And it all works out to be 5443.75. And what are the units? People, or people per year, or people per year, or people years? Just people, right? It is the actual average population during those years was that many people. How do you get 3/4 of a person, Phil wants to know. You have to wait and take Calculus 2 to figure that out. Do you think that the average number of people in a family in the world is an integer? That would be very, very unlikely for that to happen. Any questions on that one? And then the last thing we used integrals for was those equation of motion problems. Remember those? Acceleration, velocity, position. So here we go, our last question. You're driving along at 80 feet per second. When you see a dog sleeping in the road, a 110 feet ahead of you, if you put on the brakes, which of course you will do, you can decelerate your car at a rate of 30 feet per second. What's the question? Do you avoid the dog? Can you save the dog? So with these problems, we've decided it's easiest to start with which function? Acceleration, velocity, or position? Acceleration. So we know a of t, in this case, equals what? 30 feet per second, because you're speeding up as you head towards the dog. Minus 30, you're slowing down. We think that's what happens when you put on the brakes. So from acceleration, we can get to what function? Velocity is the antiderivative of acceleration. So do you know a function whose derivative is negative 30? Negative 30t, but it's not the only one. Plus c. Do we have enough information to figure out what c should be? Yes, because we know the velocity at time 0 ought to be what? Ought to be 80. And then from velocity, we can get to position, right, by integrating velocity. So what's the integral of negative 30t? Minus 15t squared plus 80t plus d. And now we don't know officially where we are, but we can choose d to be something convenient. We could choose d to be 0, in which case the dog will be at position what? 110, right? If you chose d to be 5, the dog would be at position 115. So you can choose d to be any number you like, and then the dog will be 110 feet ahead of that. So let's just say that d is 0, and we'll just say minus 15t squared plus 80t. It doesn't matter whether you include the d or not, you get the same answer every way, because the dog is going to be at position d plus 110, right? Even if you leave the d in there, it'll still work out. All right, what do we do? We figure out t from the velocity, because we're going to figure out when do we stop, right? So how do we figure out when do we stop? Right, you stop when velocity is 0. So t is 8/3, I think, 80 over 30. All right. What do we do with our 8/3? Plug that into S, right? So negative 15 times 8/3 squared plus 80 times 8/3. It's getting very stressful. Negative 15 times 64 over 9 plus 640 over 3. 15 over 9 can simplify to 5 over 3, right? So we have a common denominator of 3. So negative 5 times 64 is negative 320, plus 640 is positive 320 over 3, which is 106 2/3 feet. The dog lives. It was just 3 1/3 feet away, but the dog survived. Tanya would like to know, do all of these kinds of problems like this last one take the same steps, going from a to v to s? Yes, they do. We start with the easiest function, integrate, and integrate again. Yes, question?
Yeah, Professor, if you are riding a fighter jet.
Driving a fighter jet, yeah?
And then shooting a bullet from the fighter jet down.
Yeah.
What would be the velocity as it goes in the direction of gravity?
The question is, if you're in a fighter jet and you're shooting a bullet from the fighter jet, and you're shooting the bullet forward or you're shooting it downward? You're shooting it downward? Well, then we need to know, and you're asking for the velocity in what direction? Straight up and down? Yeah, so then you would need to know the initial velocity of the bullet leaving your gun, and you need to figure out this is not a problem that we would do, because you need to figure out the component of that velocity. You said which, downward or forward?
It's not really like down like this, but...
I know, but you want to know the velocity relative to what? Relative to the ground or relative to the plane? Or all of those have different answers. But in any case, we won't have to do any such complicated problems like that. But let me just say, you might think that it was obvious that the dog was going to live, right? Because who would write a problem where the dog died? Another book that I used to use in this for Calculus 1, at the end of every chapter, there was a problem about a spy. And in the first case, the spy is flying a fighter jet, and he falls out. And does he pull the parachute in time to avoid dying? And you do the calculations, yes, he does. And then again, look at that. In chapter 2, there's the spy again. Now the spy is in some chamber and poisonous gas is pouring in. Can the spy untie the knot in time? And you do all the calculations, yes, the spy barely makes out in time. And you keep going. Every problem at the end, there's the spy in some dangerous situation, and the spy lives. And then finally, we get to one of these chapters. This is like chapter 10 or something in the book. There's a problem like this. The spy is driving in the desert. He sees a camel in front of him in the road. He's driving his really fast car. You do this very same thing, and you think, I must have made a mistake, because actually, this number ends up being more than the distance to the camel. But then you open the back of the book, because it was an odd-numbered problem, And what it actually says, the answer in the back of the book simply is, and they might not say this today because things are much more animal friendly, but it simply says, the camel is toast. That's what it said at the end in the answers at the back of the book. All right, everyone, happy studying. Thank you for coming.